Right now, behind massive concrete walls like Hoover Dam, trillions of gallons of water are pushing forward with enough kinetic pressure to wipe entire cities off the map. Yet the terrifying reality most people never realize is that if engineers built a dam completely solid and watertight, the entire structure would blow apart and slide down the canyon in days. Every single massive concrete dam is deliberately designed to leak from the inside on purpose, and those dark, cold tunnels winding deep inside the concrete are the only reason millions of tons of water stay trapped behind the wall instead of leveling everything downstream. To understand why a dam has to leak to survive, you first have to grasp the brutal physics of hydrostatic pressure, because water does not behave like a pile of dirt sitting against a wall. When you stand in a swimming pool, the water pushes against your chest with a gentle, comfortable resistance. But when you stack that water hundreds of feet deep inside a mountain canyon, water pressure increases by nearly half a pound per square inch for every single foot of depth. Near the surface where boats cruise, pressure is practically zero, but down 700 feet below, every square foot takes tens of thousands of pounds of crushing force. This creates a colossal triangular wedge of hydraulic pressure that wants to do two catastrophic things: push the concrete downstream like a hockey puck across ice, and tip the entire dam forward like a falling tree. Engineers combat this force using two completely different philosophies of physics, depending on canyon shape and bedrock geology. The first approach is the classic gravity dam, which relies on pure brute force. In a gravity dam, engineers pour millions of tons of dense concrete, shaping it so the sheer downward gravitational pull of the structure is significantly heavier than the horizontal push of the reservoir. As long as that downward weight keeps the concrete pinned tightly to the bedrock, friction along the base prevents the lake from shoving the structure downriver. The second approach is the arch dam, an absolute masterclass in structural judo. Instead of sheer dead weight, an arch dam curves upstream into the reservoir, shaped like an archer's bow. When billions of gallons of water push against that curved concrete face, the water pressure actually compresses the concrete blocks together, squeezing them tighter and deflecting the immense hydraulic load outward into the solid granite canyon walls. Instead of the dam taking the beating alone, the canyon walls absorb the crushing force, allowing the concrete wall to be remarkably thin compared to a massive gravity dam while holding back just as much water. However, whether a dam is curved into the canyon walls or relies on millions of tons of brute force concrete, every dam faces a hidden predator that nearly destroyed early dam engineering: hydrostatic uplift. No matter how smooth concrete looks or how solid bedrock appears, neither is an impermeable sheet of plastic. Microscopic fissures, rock fractures, and cold joints run through the foundation. Under hundreds of feet of water pressure, the reservoir forces its way into those microscopic cracks, creeping directly beneath the base of the dam. When high-pressure water gets trapped underneath the foundation, it pushes upward in every direction, acting like a giant hydraulic jack under a car. This upward pressure directly fights against the downward force of gravity, effectively making the multi-million-ton concrete dam feel lighter and lighter. If uplift pressure builds unchecked, the friction between the bottom of the dam and the bedrock drops to near zero, and the entire structure can instantly break loose and slide down the riverbed in seconds. This terrifying phenomenon is precisely why every modern dam is deliberately built to leak from the inside out. Past the restricted doors on the crest, steep elevator shafts plunge hundreds of feet into the freezing, echoing belly of the dam. Miles of concrete inspection galleries wind through the interior, lined with rows of deep vertical holes drilled into bedrock. These are pressure relief drainage holes, and their entire job is to give trapped seepage water an easy, low-resistance escape route. When high-pressure water creeps beneath the foundation, it hits these drainage holes first, relieving dangerous pressure and trickling into concrete gutters. From there, gravity and industrial sump pumps carry the harmless, low-pressure drainage water out to the downstream riverbed. This continuous trickling is not a failure. It is the dam breathing, bleeding off uplift so the monolith stays anchored. To ensure water cannot simply bypass the drainage holes and wash out the canyon walls, engineers install another critical invisible defense known as the grout curtain. Before the first block of the dam is poured, specialized drilling rigs bore a tight line of deep holes straight down into the riverbed, extending hundreds of feet into the bedrock and canyon walls. Crews pump thousands of tons of liquid cement grout into these holes under intense pressure, forcing the grout into every natural crack and fault line until the rock becomes completely solid and impervious. This underground grout curtain forms a massive subterranean barrier directly upstream of the drainage holes, forcing underground water to take a long, high-resistance path that drastically slows it down and kills its energy before it ever reaches the dam foundation. Even after mastering water pressure, engineers face an internal enemy that comes from the concrete itself: extreme chemical heat. When you mix Portland cement with water and gravel, it triggers an exothermic chemical reaction called hydration that generates an unbelievable amount of heat. In a standard house patio, that heat radiates into the air without an issue, but when pouring a concrete monolith hundreds of feet thick, the heat gets completely trapped in the center. The core of a massive dam can easily exceed 150 degrees Fahrenheit, and if left alone, that concrete would take decades to cool down naturally. As the exterior of the dam cools quickly in the night air while the interior remains scorching hot, uneven thermal contraction would tear the concrete apart with massive structural cracks, destroying the dam before the lake was even filled. To prevent this, engineers never pour a dam as one continuous wall. Instead, they pour the dam in thousands of individual interlocking columnar blocks, and inside each pour, they embed miles of thin-walled steel tubing. During construction, refrigeration plants pumped ice water through those tubes day and night, cooling the blocks so crews could grout the joints permanently. Once the structure is cooled, locked, and holding back a massive reservoir, engineers face the most dangerous operational threat in civil engineering: the spillway. The golden rule of dam safety is that water must never, under any circumstances, be allowed to spill over the top of a concrete dam in an uncontrolled sheet. If water pours over the crest, the falling torrent acts like a hydraulic hammer, scouring the bedrock at the toe of the dam, eroding the canyon walls, and undermining the very foundation keeping the structure upright. To manage heavy floods and snowmelt, dams rely on engineered spillway channels and massive intake gates designed to bypass excess water around the dam and discharge it safely downriver. However, moving millions of gallons of water down a concrete chute at 80 or 100 miles per hour summons an invisible, violent monster known as cavitation. When water accelerates down a steep spillway, tiny surface imperfections in the concrete, even something as small as a quarter-inch bump or joint seam, cause the high-velocity water to separate slightly from the surface. In that microsecond of separation, localized fluid pressure drops so drastically that the water literally boils at room temperature, forming microscopic vapor bubbles. As these bubbles are carried downstream into zones of higher pressure, they instantly and violently implode. Each individual bubble implosion generates a microscopic shockwave with localized pressures exceeding tens of thousands of pounds per square inch, acting like tiny sticks of dynamite hammering against the concrete. Over a few hours of high-speed flow, cavitation can chew through 3-foot-thick steel-reinforced concrete slabs like soft cheese, digging into the subgrade rock beneath the chute and threatening to trigger a catastrophic hillside collapse, exactly as the world witnessed during the 2017 Oroville Dam crisis. Modern spillways solve this with aeration slots along the floor, introducing tiny air bubbles that cushion against implosion shockwaves and shield the concrete. Beneath all this high-speed water action lies the silent clock that threatens the lifespan of every dam on Earth: sedimentation. When a mountain river flows naturally, it carries millions of tons of sand, gravel, and rich organic silt. The moment that fast-moving river enters the calm waters of a reservoir, water velocity drops to near zero, and all that suspended sediment settles to the bottom. Over decades, a massive wedge of dense mud creeps toward the dam face, burying low-level intakes and adding immense deadweight pressure. Engineers constantly battle this sediment using deep, low-level sluice gates, regular bathymetric sonar surveys, and complex hydraulic flushing operations to scour mud away from powerhouse intakes, ensuring underwater gates stay clear and functional so the dam can continue generating clean hydroelectric power and releasing municipal water for downstream communities. When you stand on top of a towering concrete dam looking out over miles of blue water, it feels like the most permanent, immovable object ever constructed by human hands. But the reality is that a dam is not an inert, rigid barrier. It is a living mechanical structure, constantly flexing with temperature changes, bleeding off destructive hydrostatic uplift pressure through its internal arteries, and cushioning explosive fluid shockwaves along its spillways. It does not hold back the sheer power of nature by being completely stubborn and watertight. It survives because human engineering learned how to give water a controlled path to escape, letting the dam leak safely on the inside so it never fails on the outside.